Thank you very much for the invitation to come speak at this nice workshop. And it's always a pleasure to be here in Princeton and at the Institute. So as you see, I'm talking about something that's actually a little bit askew from the actual name of the workshop, but of course it has a lot of connections with the sort of arithmetic side of this world. So hopefully those will emerge. So let me begin, since a lot of people here are in representation theory, automorphic representations, just by mentioning the roots of this theory, or the idea of where it's coming from, and that is that the theta correspondence, which is something I studied for many, many years with Steve Rollis and other people, and of course many other people have contributed huge amounts here, people who are here, Wells Bourget and so on and so forth. Anyway, it's a basis, it's been used as a tool of study of automorphic representations and also representations of local groups over local fields. And on the global level, the way this is usually done is that you construct theta functions in two variables. So G and H are my dual pair, groups in a dual reductive pair, and G and H are variables in those groups. And then you make theta functions, which are then functions of two variables. Phi here is a Schwartz function in some, for example, Schrodinger model of the Weil representation. And then you can use this thing, which is practically an automorphic form in the two variables, as an integral kernel to transfer automorphic forms from one group to the other. And so this was done for many, many years, and there are a tremendous amount of interesting phenomena have been uncovered this way. It's been very well studied. But anyway, the overall pattern, which is familiar probably to many people here, is that you can use the Siegel formula. So for example, a typical question is, when is it this theta lift when you integrate non-zero? And there's a famous Rollis inner product formula which comes out of some combination of the Siegel-Weil formula, the doubling method that connects with the L function, seesaw identities, and eventually you connect the non-vanishing of these theta lifts to the special values of L functions together with local obstructions. This is sort of a fairly familiar pattern in the theory of automorphic representations. And so as a slight variant of this, John Milson and I considered the case where G is a classical group, OPQ, UPQ, and SPPQ, and we constructed the theta functions which are valued in the de Rham complex of, so D here is the symmetric space for the group G, gamma is an arithmetic subgroup, so here we are, a locally symmetric space. So John Milson and I constructed theta functions which were valued in the de Rham complex for these manifolds. And these, I like to call these geometric theta functions. They've proved to be very, very useful over the years. And they're closely linked to certain type of locally symmetric cycles in the manifold, either geodesic or Riemannian submanifolds inside of M, gotten mostly by taking some subsymmetric spaces of D and folding them up, looking at their images and so on. And so the nice thing about these geometric theta functions is they're actually closed as differential forms by the construction. And so you can pass to their cohomology classes. They will define cohomology classes with values in M. And so also they give rise to a theta correspondence which starts with an automorphic representation, for example, of the other group in the dual pair. Remember, H was the other group. And by integrating against the kernel, you end up with a map from automorphic forms on H to cohomology on M. So this is sort of a cohomological version of the theta correspondence. And so such correspondence is a starting point for many applications, and I just mentioned the relatively recent work, time flies, of Bergeron, Milson, and Meuglin, where they, among other things, establish in the case where M is a Hermitian symmetric space, so for UN1, for example, for ball quotients, M is a quasi-projective variety, and these cycles I mentioned up above are actually algebraic cycles, and they were able to use this machinery together, of course, with work of Arthur and a lot of serious other input to establish new cases of the Hodge conjecture for these manifolds. So this is a very powerful tool. Of course, here it's combined with many other tools, but still, this is one of the main ingredients. So for a long time now, as it says here on the slides, I've been pursuing the notion that there's what I call, you might call a third generation of theta functions. I've sort of illustrated two generations there, the classical ones, the geometric ones, and now these so-called arithmetic theta series. And so roughly speaking, these arithmetic theta functions should arise when the Shimura variety M, or M is a Shimura variety rather, and you have a regular integral model of M. So now we're going toward an integral theory. And the idea is to construct generating series, these will be the theta functions, associated to certain special cycles in, notice this is the script M, this is the arithmetic, or the integral model, And we want these to be related to, these special cycles to be related to classes in the arithmetic Chow groups, which very conveniently Xiaowu already softened up the audience with a lot of discussion of these arithmetic Chow groups. So these play the role of the cohomology groups, but for these regular integral models. And so the goal is to try to imitate somewhat the theory that Milson and I had done earlier, where we had constructed some kind of theta functions valued in cohomology groups. Hertzebruck and Zagier, of course, was the origin of this whole thing for us. But the idea is to construct theta functions where the coefficients are lying in these Chow groups, and at the same time they're automorphic forms or modular with respect to the other group H. And if you could construct such things, then what you would be able to do is to define an arithmetic theta correspondence. So now, taking an suitable automorphic forms on H, you could integrate against these kernels and end up with classes in the arithmetic Chow group. And then the dream would be that the non-vanishing is connected with an arithmetic Siegel formula, and that the non-vanishing conditions will now be related to derivatives of L functions plus local obstruction. So that's the sort of overall scheme of things. Of course, it's very vague, and anyway, with that as background and motivation, what I want to discuss today is some recent work of a joint project with Jan Brenier, Ben Howard, Michael Rappaport, and Tonghai Yang. This was part of an AIM squares project, so we had a slightly extended square. I think maybe it was a pyramid. I'm not sure who was at the top of the pyramid. But anyway, the groups, roughly speaking, in question are going to be, let's press the right button. G is a unitary group of the type that we've seen several times in this conference, and H is going to be U11, so that's the dual pair in classical language, and we'll see how it develops in this arithmetic language. Here are the two preprints that are contain the results. The first one, the modularity of these theta functions, the construction of the theta function, and the second one contains some applications to arithmetic of roughly of the sort that I just mentioned. So there's way too much in here to talk about in a talk, so I'm going to mostly concentrate just on the construction of the arithmetic theta series as an illustration of the kind of techniques and methods and issues that are involved in these things. So anyway, these papers build on the work of a number of subsets of the authors and many other people as well. And so this was a list of some of the preliminary or background papers that are being used here. So one of the reasons for making this big list, and of course it could make it much, much longer if you took the bibliography to the paper and just put it up there, is that there are a number of points as I discuss the mathematics where I'm not going to try to cite where in which point in these papers these results are proved, so that there's attributions are going to be blurry. They're just within this whole thing. So not everything I'm discussing is literally in the two preprints that I mentioned earlier. Okay, so now let's start in. So I first want to discuss the unitary Shimura variety. So I start with an imaginary quadratic field. Notice this, so the discriminant is minus d, and this is odd. So the fact that 2 is unramified in the extension is a useful fact. It simplifies some things. I don't think it's essential in the long run, but these papers are long and hard enough already, so okay. This simplified a number of things. Anyway, so now what you do is you fix a pair of Hermitian spaces, but notice it's not the Gann-Gross-Prasad situation where this W0 might be dimension one less, but instead W is a signature n-1, so it's dimension n, signature n-1, 1, and W0 is simply signature 1, 0. So it's simply a unary quadratic form, so it's just a copy of the field with the norm form scaled by some scalar, and it will play some kind of auxiliary role, but it'll be very, very important, it'll turn out. So the group G will be the subgroup of the similitudes where the two scales are equal. And then we're also going to fix, as part of the input data here, self-dual lattices in these two spaces. That's some kind of condition, perhaps, on the Hermitian forms. So that's being imposed here. And then we let K be the stabilizer in the similitude groups of those two lattices intersect with this slightly diagonally embedded group where there's a linkage between the scales. And finally, out of that data, you get a Shimura variety where D here is actually, I'll discuss more, what is a complex ball of dimension n-1. So you get this Shimura variety. And I should mention, why is it that there's this extra factor W0 in here? Right now, it just looks like extra stuff, but when we go to define the special cycles at an arithmetic level, we'll see it plays a really absolutely essential role. And I should mention one other funny thing, and that is that in this business here, I may mention it again later, but I thought while I'm thinking about it, I'll mention it now. If you had just taken GU, there's a sort of standard model, there's a standard Deline's H for such a thing attached to abelian varieties of signature n-1, and the standard Shimura variety. Dick Gross, several years ago in a letter to Deline, had mentioned that there was another funny H that could be used in this situation, and he asked whether or not there was some moduli interpretation of it. It didn't seem on the face of it that there was, and it turns out that this addition of this extra factor here exactly realizes his H, so that in fact this is kind of an answer to that question that he had. We'll see that this is a moduli space for abelian varieties, and moreover it turned out that we had discovered this or found this extra factor to be necessary kind of on our own, and well, it turned out to be just matching his speculation. So now we're going to define the integral model, and so we have to go to a moduli problem for abelian varieties. So OK, of course, is the ring of integers. I don't know if the laser isn't working now, I think. Oh, there it is. OK. So OK is the ring of integers of the field K. And so what we're doing is looking at this moduli problem. So we're looking at essentially, you can erase schemes if you don't like it. These are abelian schemes, so a family of abelian varieties over a base over OK, blah, blah, blah. Anyway, abelian varieties of dimension n on which OK is, action of OK is given. And there's this determinant condition which describes how the elements of OK act on the Lie algebra. And so this is just saying that if you looked at, say, a complex abelian variety and the action of OK on that complex abelian variety, that you now have a n-dimensional complex representation of the field K, if you like, and we're requiring that it be n-1 copies of the standard embedding, which I forgot to mention but is fixed here, and 1 copy of the conjugate embedding. So that's a description of how this thing is supposed to act on the tangent space. This is, of course, now imposed sort of globally on the abelian scheme. These are principally polarized, and the Rosati involution attached to the polarization is supposed to induce the complex conjugation on the field K. So this is the data. Now this is well, you can define a moduli scheme this way. So this is representable by some stack, and but the problem is that it's not quite good enough at the ramified primes, and so one has to improve it. So I'm going to be slightly too detailed about improving it, but you can just ignore it. I mean, the point somehow is that this guy as it stands is not regular. It's regular outside of the primes dividing the discriminant, but the primes dividing the discriminant is still not so good. So you now have to make a better model, and now what you do is you add, for those people interested in technicalities, you end up adding a sub-sheaf of the Lie algebra on which OK acts by the standard embedding into its structure group, I mean the structural morphism, and on the quotient it acts by the conjugate. So this is like an n-1 signature condition, but given physically in terms of giving the line bundle a sub-bundle on which one part of the action is realized. And that turns out, when you have ramification, and it's hard to tell the difference, mod p, between alpha and alpha bar, because it's ramified, then this turns out to kind of fix that. Okay, so anyway, the resulting moduli stack, which is called, this is due to Kramer, a student of Rappaport, the resulting model we'll denote by M, Kra, and so on. So this is regular and flat over spec OK. So this is the nice moduli schema that we're going to work on. Now remember, in the original Shimura variety setup, there was both a W and a W0. So now the analog of the W0 pops up. So we let M10 be defined analogously, exactly the same as on the previous slide for n-1, except now I have elliptic curves or elliptic schemes where the action of OK is by the standard embedding. That's the signature. And they're principally polarized, et cetera. And so this is already smooth over spec OK. So no additional work is required to make this guy into a nice smooth, in fact, smooth stack. So what we now do is consider, well, here I'm looking at generic fibers. So notice the script here, and these are regular. So this is just the generic fiber of those two moduli problems. And so, of course, you can take their product. They're both schemes over K. And if you take their product, the Shimura variety mentioned earlier, its canonical model is sitting inside of there, and it's an open and closed subthing. So there's a number of components of this thing. And so basically what you do is you require that the Hom space from the Tate module of the A0, which is the elliptic curve, to the Tate module of the abelian variety, this Hom space, be isomorphic to the ZL extension of the Homs of those lattices that were fixed earlier. So that's kind of a framing condition, and what it does is inside of this moduli scheme, the product, it picks out an open and closed substack. So that's, and that, which, well, that's what I'm saying happens on the generic fiber, and now you do something analogous in general, so okay. So now to get our integral model, what we're going to do is take the Zariski closure. So you see what I've done now is inside of this, I'm getting a feeble dot here anyway. So you see the Shimura variety is sitting inside of this product of, these moduli spaces. And see if I have another pointer here. Oh. Is this any better? Yeah, okay. So the Shimura variety is sitting inside of this. Okay, just in case. Okay, I've needed to beat back the audience, I guess. Later. Okay, anyway, the point is the Shimura variety, remember, is this open and closed subthing, this product of these two unitary Shimura varieties. They have integral models. Now here, there's a model where we don't go all the way to that subspace, et cetera. There's some other condition, a so-called Pappas condition. And we take the, so it's a little tricky here, but it's relevant later. And that is that what we do is we take inside of this integral model, where we use this Pappas model, which I'll mention a little bit more about in a moment, we literally take the Zariski closure. So this is some alternative integral model that's not regular. We take the Zariski closure of this guy and get in here. So this defines this guy. So I have my Shimura variety, I take its Zariski closure in this scheme. And now what happens is that in fact, as I sort of trying to stay in a few words here, this Pappas model is almost regular, but there's a finite number of singular points in the fibers dividing, for primes dividing the discriminant. There's a few bad points, and you have to, there's some singular locus inside of here, and what you do is you blow up that singular locus. So there's a final step here to get the actual model we want, where we blow up, this blows this up. The Kramer model blows up the Pappas model, so we get a blow up here. So our final model that we're going to work with has got a Zariski closure aspect, but then there's some exceptional fibers, which are the inverse, I mean, the full transform of the blown up points, okay? So there's some exceptional locus in there. Now, let me also say one reason, I mean, people have looked at these slides and said, oh, way too many details, et cetera, et cetera. So let me make an excuse, okay? Here's the excuse. For many, many years, I've talked about these kinds of things in a very vague philosophical way. Then roughly you do this, and hopefully take care of the compactive, and et cetera, et cetera. And so today, that's exactly what I'm not doing, okay? This is really a theorem. All the I's have been dotted, all the T's have been crossed, all the bad singularities in the special fibers are taken care of, et cetera, et cetera. So this is a completely precise theorem, not a vague, I hope like this could be resolved talk. So that's why there are the details, which of course can be squinted at and removed if you want the other kind of talk to come out, right? Okay. So anyway, the footnote not quite means that simply that we're not taking the Zariski. Not quite. Well, you could, yeah, okay, that could be a comment on my comment, right? Okay. See, I have a very sharp audience here. He should sit in the back anyway. We can't see the footnotes. All right, anyway, so here I'm explaining something about the Pappas model, and that it has some bad points blown up in the Kramer model. Okay, so there's two models. Mostly we'll work on this one. Occasionally we'll work on this one. I explain why in just a moment. Overall, the upshot of all that previous discussion is that we now have this nice model, which is a regular model, and it lives over this one, which is almost regular except for a small number of singular points, and they're related by a blow-up. The exceptional fibers will play a role a little bit later. Okay, they both have nice toroidal compactification, so you can compactify these varieties by adding some boundary divisors, which I'll discuss in more detail in a little bit later. Anyway, the reason I'm explaining here why it is we carry along both models, and that is that the problem is that the main issue here is going to be how to get the divisors of functions which you somehow construct in an automorphic way on the generic fiber, how to compute their divisors on the integral model. And the problem with the Pappas model, or with the Kramer model, is the fact that there are these components of in this model there are these components, they're vertical fibers, which you cannot detect very easily because on the generic fiber. And we need to control those. And so on the other hand, this guy doesn't have that, disadvantage. There you can sort of have a better way of getting a grip on things. So we carry them both along. That's why. Okay. Okay. So anyway, for the moment, I'm going to drop the subscript and just write S star for the compactified model of this guy. And so, so this is a nice regular proper over OK, spec OK. Right? So there's a place where you can do arithmetic Chow groups. It's a nice regular model, as was mentioned, and hope to do arithmetic intersection theory, et cetera, et cetera. Okay, so now I want to discuss the divisors, which is what we're going to discuss, not higher codimensions. So the point is that this model S, this is one S, this is another, an S-valued point of this guy corresponds, among other things, to a couple of abelian varieties. So this is an elliptic scheme over the base S. This is an abelian variety over the base S with the properties we mentioned earlier, with OK action and the additional equipment I discussed earlier. And now attached to such a pair, you can consider the OK linear homomorphisms from A0 to A. And it turns out that this space has a natural Hermitian form on it, defined using the polarizations. Namely, if I have a pair of homomorphisms from A0 to A, I apply X1, I apply the principal polarization, which is an isomorphism here. I come back by the dual of X2, and then I come back by the inverse of this principal polarization, which is an isomorphism here. Altogether, you get an OK linear endomorphism of A0. But of course, A0 is an elliptic curve with an OK action. And so if you have an OK linear endomorphism of such a thing, it's an element of OK. It's given by a multiplication by something in OK. So you simply take that element of OK, and that altogether defines a Hermitian form on the space of such homomorphisms. So there's a very natural construction of a Hermitian form. And this turns out to be positive definite, so it's a nice Hermitian form here. And in some funny sense, when I talk about arithmetic theta series, these theta series are attached to, in some ways, these lattices. So a theta series should be attached to a lattice, and you'll see in some moral way, not that this is a given lattice, because I'm now going to vary over a moduli space, et cetera, et cetera, et cetera. There's not one fixed lattice, but nonetheless, you can think of these arithmetic theta series are attached to this lattice, or this lattice viewed as some kind of something on the moduli stack. Okay. So now to get the cycle, so what you do is you simply consider the cycle to be, for a fixed integer m, you consider the triples A0, A, and X, where X is an element of this lattice. In other words, a homomorphism from A0 to A, OK linear, whose inner product with itself is m, the fixed integer m. Okay? And so this is, so you consider the triples like this. So if you equip, so this would define some sort of a cycle, and it maps to S, and this is a finite unramified morphism. So it's a, you can morally think of it as simply a divisor inside of S. And so these are some kind of analogs of, say, Hertzsprung-Zagier divisors, et cetera, et cetera, et cetera. Okay? So these are Cartier divisors on S. And so you can think of them as the loci inside of this S, which is a moduli for pairs A0A, where the A0 has a way of being incorporated into A in this way. So the A0, the A in particular, splits off a CM elliptic curve. So this, having the fact that it has an extra factor in a specified way, is a strong condition. Okay. Okay. And now we let Z star be simply the Zariski closure of this thing in the toroidal compactification. I'll come back to that in a minute. So we have a cycle for each m. And now what about the compactification? So let's go back to our generic fiber. On the generic fiber, we just have this locally symmetric space. And D, remember, or I didn't say, but now I'm saying it more precisely, is the negative lines in a space VR, in a complex vector space. But the complex vector space is this one, HOM W0W. And it's exactly here where, again, Gross's H comes in, because you can think of this as two Hodge structures, but we're taking the tensor product that is a different type. Okay? So D is the negative lines in VR, where this has got this Hermitian space like this, a Hermitian form like this, as was defined for the special cycles. And so, as I mentioned here, the W0 is playing the same role as the A0. So you see there's some parallel construction here. So the rational boundary components of this locally symmetric space are indexed by the isotropic lines in VR. So you see, of course, a negative line, if I take the closure of the negative lines in the projective space of all lines, on the boundary I see isotropic lines where the Hermitian form is simply 0 instead of being negative. And we only want the rational ones, just like in the upper half plane. You don't take all the points in the real numbers, you take only the rationals. So here again there'll be irrational isotropic lines. So these are rational boundary components corresponding to isotropic, as I said, k lines inside of this V, which is a k vector space. And so to each such line, so the cusps, since this is an adelic quotient space, to index a cusp I not only need a rational boundary point of D, but I also need some G which tells you which coset, which offset you're in. So that means that the cusps are actually indexed by pairs consisting of a rational isotropic line and an element of GAF, which tells you where you are inside of the adelic quotient, modulo some equivalence, which I won't write down, but you could figure out right now. Anyway, associated to such an isotropic line, we get a filtration. So attached to such a boundary component, we get a filtration. So you can consider it's an isotropic line, so its orthogonal complement inside of V contains J. So this is just a filtration gotten from an isotropic subspace. And then this is as isotropic rational subspaces, but there's an integral version because there was a lattice L. So the lattice L is, or GL better for the adelic thing here, is this HOM from GA0 to GA. So the group G acts on both those lattices that we fixed as part of our initial data, moves them around in the usual way adelic stuff acts on lattices. And so we get, for each G, we get a lattice, and then you can look at the interaction between that lattice and this filtration, and you get some lattices like this. So in particular, what you get is you take this lattice here and you mod out by this isotropic lattice, you get a lattice attached to the cusp, phi sub L, which is then positive definite of rank n minus 2. So each cusp has a positive definite lattice attached to it. And so I still want to tell you how to compactify. Well, I'm still on the complex fiber, so I'm still explaining that part of the theory. If I take the Bailey-Burrell compactification of this thing, what happens is you simply end up with points added in for each one of those isotropic boundary components. It looks like the upper half plane with the points. But of course now the whole thing is dimension n minus 1 and the points are points, so things are badly singular at these points. And so you blow up these points. This is how toroidal compactification works in this situation. And what you get when you blow them up to make a nice model is you end up with these particular abelian varieties. So what you do is you take the universal CM elliptic curve over this moduli space of CM elliptic curves, and you tensor it with this lattice. This is sort of sometimes called the Sayre construction, where you can tensor an elliptic curve with a lattice, and you get an abelian variety of dimension n minus 1. In the complex world, I take here I can do this integrally. So this scheme, this is really, I'm being sneaky here and stepping ahead. This is actually the integral version, and there's a universal integral E, and this becomes an elliptic or abelian scheme over spec OK. But here I'm taking the complex points, and that's what you glue in here to make the smooth compactification. You blow up the cusps into such a thing. And so now the key point here is that this description of the desingularization of the Bailey-Burrell compactification, the generic fiber, sort of propagates to the integral model in the sense that now I have these elliptic or abelian schemes, which I can then mod out as a stack by this finite isometry group. There was a filtration here, and the middle, that lattice has a big isometry group. This lattice can have a big and quite beautiful isometry group, which are playing some role here. And so you can take an orbifold quotient of this abelian scheme by this discrete finite group, and that's what you end up adding in to get the compactification. This is now integrally. So the picture is this. The toroidal compactification is the original guy together with a disjoint union over the different cusp data like this, modulo the equivalence, which I let you work out for yourself, of these blown up, or these abelian schemes. And so the boundary is a smooth divisor, which is actually flat over OK. OK, so this tells you what S star looks like. And now what happens is I'm trying to, by the way, what am I doing here? You might ask. I might ask. What I'm doing here is I'm going along and I'm going to construct the arithmetic theta function. It's going to be a generating function for the classes in the Chow groups of these cycles which I'm constructing. So there'll be classes in Chow hat 1 attached to these various ZMs, and then I'll make a generating function. That will give you the generating function question. So just to look ahead. So I'm still fiddling around with making these cycles. So we remember we took the Zariski closure of this guy, which is defined inside of S star. So this is a nice divisor inside of here. But what we're going to do to it is add a certain amount of the boundary components. And here's what you add. For each m, you look at this combination. So here you see for each cusp, there's a lattice, which is positive definite. I can look at the number of lattice vectors of length m, multiply by this rational number, and multiply that boundary component by this factor. So that's the mth, and we sum over the boundary component. So this is the mth additional piece, and so this is our total divisor. So it's something gotten from the Zariski closure together with some components which are strictly components of the boundary. Okay, as I said, I'm trying to be precise here as opposed to. Okay, so now we're going to define the arithmetic theta function. So the idea now is that we're going to make take these cycles, which I've just defined here. We're looking at their classes in the arithmetic Chow group. So notice there's a hat here. So I still have something to discuss, namely Green's currents or Green's functions. But anyway, we're going to make this generating function like this. These are the classes which we saw on the last slide, except they're now going to be equipped with Green's functions. And they're going to be this thing is going to be a Q series. I should have put a bold Q, double brackets Q here. This is just a formal Q series, so there's some typo here. But anyway, these classes are going to be classes in the arithmetic Chow group of that nice regular model. Okay, so what's remaining in terms of issues? Well, first of all, there's this hat, which means I have to add on some Green's functions, which I will discuss a little bit later. And the second point is there's this constant term when m equals 0, because then this definition I gave you in terms of moduli doesn't apply. So let's start with the constant term. And here I'm just reminding you of what it is that I have to do in order to pass from an actual divisor on S star to a class in the Chow group. I need to equip it with a Green's function, which satisfies this Green's equation here. And I'm doing this in the Gillet-Soulé style, so I'm not being careful about a harmonic representative and everything here. You just take anything you get on the right-hand side here. Later on, there'll be some specific choices made. And anyway, the relations are given by taking rational functions on S, looking at their divisors on the scheme S, and then taking minus log absolute value squared of that meromorphic function. So those are the relations. Okay, so now what about Z0? So this arithmetic Chow group can be viewed as metrized line bundles, which we saw already in Xiao's talk this morning. And so I'm going to construct Z0 by constructing the line bundle, or telling you what the line bundle is. So remember, D is the space of negative lines in VR, so it's an open subset of the projective space. And I can pull back the tautological bundle here, and I get a perfectly nice bundle on D, which is equivariant for all group actions, et cetera, et cetera. Therefore, it descends to the Shimura variety. And I want to put a metric on it, but you see, if I have a negative, this is the fibers of this are the negative lines. And so that means if I take the Hermitian form on V, R, and restrict it to one of these lines, it's negative definite. If I change the sign, it's positive definite. And then I'm going to rescale that metric. So that's giving me a metric on the fibers by this weird constant, and where gamma is the Euler constant. And it turns out that this bizarre choice plays constantly a role in RK-Love theory and in these kind of modular RK-Love things. And I have no idea why. So there's gamma, whatever it is. But that's what is forced on you if you want these theorems to be true. Okay, so anyway, there's a natural way of extending. So here I've told you what the line bundle is on the generic fiber. On the Kramer model, you can express it using the Lie algebras and this extra data which was given on the Kramer model. And then there's a way of extending to the boundary, which is even too much detail for me, so I'm not going to mention it. Okay, so there's a line bundle, and it's a metrized line bundle. In fact, I told you what the metric was. And so it turns out that this metric on here extends to a metric with singularities along the boundary. And so we're actually using not the classical Gillet-Soulé groups here, but the slight variant or the improvement of them due to Burgos, Kramer, and Kuhn, where they allow slightly singular metrics in these things. And so that's what's secretly being used here. So this metrics on this pick hat are allowed to be singular along the boundary, a little bit singular. Anyway, when we get done, we define the total class hat total 0 to be the inverse of this tautological bundle metrized, plus a little bit of stuff coming from the exceptional locus. Remember, there are these vertical things coming from the blow-up, et cetera, between Pappas and Kramer. And then here there's also the minus log D, which is, okay, so this cycle has no generic part, so there's no linkage between the two pieces here. You can add this, write this simply if you want it as this thing comma 0 and 0 comma this thing. and that's what you add on. Okay, so that's the definition of the constant term. So now I'm going to punt a little bit on describing the Green's function. We'll come back if there's time and mention a little bit more about how to get these Green's functions that are relevant here, but there is a way of attaching a Green's function, I'll come back to it, for each of these ZMs. And so an important point here is that this Green's function, its construction a little bit dictates why it is that we've added these boundary parts to the divisor, because what you do is you construct this guy on the integral, on the Shimura variety on the interior, and then you have to analyze what it does in the boundary, and then that tells you what extra cycle it needs to have in order to be a Green's function for the correct cycle. Okay.
Characterized in some way, this Green's function?
Well, you'll see in a minute. There are two choices which I like. Okay, this is one of them. The other one won't come up in the talk, but this comes out of Borcherds theory. This one. Okay, these will be explicitly constructed.
But you don't have some way of picking out besides it works in the end.
Right. I think in some way, yeah. Right. Yeah. Okay. There's not as much ambiguity here as there is in higher dimensional cases. Right. It's just a function. So there's no image of d and d bar. Right. So I mean, it really is a well-defined function, and so the ambiguity has to do with the right-hand side of the Green's equation. Right. Together with being perp to the constants. I mean, there's one integral you could make 0 or not, depending on how you want to play the game. Okay. So anyway, aside from a few details, we now can define the generating function. Here I did put in the formal power series variable that I should have in the earlier slide. And so now I've sort of defined this for you, better than in previous talks, I should say. And now the main theorem. So the main theorem says that this formal series is actually Chow hat 1 valued modular form of weight n, level d, and character chi n. Okay.
Tau is in the upper plane.
Tau is in the upper half plane, correct, right? So of course, as a formal Q series, it's just Q, but of course, as usual, I put Q is equal to e to the 2 pi I tau, and then there's an assertion that this is just the Q series. Well, so what do I mean exactly? What this really is supposed to mean is that if you have any Q linear functional on this Chow group to the complex numbers, you can apply it to the coefficients of this thing and make a series like this, and that's supposed to be the Q expansion of a holomorphic modular form of the given weight and character and so on, regardless of what alpha you take. So that's the content of the statement. Okay, and so as a formal consequence of that, what you get are a couple things. One is that if you take the subspace of this Chow group spanned by these classes, it has dimension at most equal to the dimension of modular forms like this. So regardless of the fact that this space could be absolutely enormous, when you have some very specific classes and you get some bound on this because of just the fact that it's modular, okay? That's somehow the number of degrees of freedom in the coefficients of a modular form. The other important consequence is what I had alluded to at the very beginning, and that is that one of the motivations for doing all this is we'd like to have some arithmetic analog of the theta correspondence or theta lifts. And so what one can do here is define an arithmetic theta lift. Namely, you start with a cusp form, and here we're just being conservative, but whatever. We start with a cusp form of weight n on gamma 0 d in this character. Chi sub k is the quadratic character attached to the imaginary quadratic field, and n is the n. So you'd have the power of it. So it's Nabin type or not, depending on n, even or odd. And you can make a map from here to the Chow group by simply taking f to what I call theta hat of f, which is the Peterson inner product of f with this guy here. Now, this is antilinear in f the way I've set it up. Sorry. I prefer not to put bar on tau. It's on phi, because it's a little hard to imagine exactly carefully what that means. Okay. So anyway, so what you can hope for now is that you can do various constructions analogous to classical construction in the theta correspondence, and you can hope, well, so given an f, these classes here, so what is known is that you get in this way from each f a class inside of here, and you can look at their image under various alphas, under linear functionals, and you often get special values of derivatives of L functions which tell you the position of these things sitting inside of this Chow group with respect to linear functionals that you can construct. And so, well, that was a branch of this talk which was already too long, which I decided not to go on. Anyway.
It's a special central value of the L function?
Not always central, not always central. I mean, it depends on the setup, but it's very interesting. So for example, one way, I'll just say this in the air without going into it because I see I'm clicking fast enough. One one thing you can do is you can take a totally real field and take the composite with the imaginary quadratic field. We saw that in a talk earlier. So you get a CM field. On that CM field, you take a CM type of signature N1. What does that mean? Well, you take a CM type, but you can restrict it to little k, and now it has a signature. So you require it to have signature N1. And then what happens is the moduli stack of CM abelian varieties for that CM field and that CM type embeds as a cycle. You still have to multiply by M0 and take some components or whatever. Embeds as a cycle inside of these guys. So what cycle will that be? Well, of course, the CM stack is just as a scheme over OK is atal. Okay, and so what happens is that you end up with an arithmetic curve inside of the moduli stack. And so what you can do is you can pull back one of these classes to that curve and take its degree, its arithmetic degree, and those things involve the following thing. So I have an F here that was an input. It turns out there's an Eisenstein series of weight 1 on this real quadratic field that I used in my construction. It's an incoherent Eisenstein series in the sense that it vanishes at 0. There's an S in it a priori. It vanishes at 0. You take its derivative, pull it back to Q. So notice I'm on a real quadratic field, but I just take the diagonal embedded upper half plane, and inner product with F, that's the answer. And so you see that's a kind of unknown Rankine integral, because if I take a totally real field of some high degree, if n is big, no one knows what these integrals are, but they're coming up as special values of some kind of pairing here. Okay. Anyway, that's the kind of thing that gets out, and it's very experimental at this point. We have the machinery set up to start doing these calculations. Some were done in a more ad hoc fashion earlier, but anyway, this is where we're exploring with this business. So where I want to go now is I want to give a sketch of the proof of the main theorem, which is the foundation for making these kind of constructions possible. And so the basic idea of how to prove modularity for these kind of series goes back to this paper of Borcherds, where he does this for Chow groups for modular curves, or ON2 Shimura varieties. And so you have the following criterion, which really is an incarnation of Serre duality. So in some sense, modular forms, are going to be dual to sections of data at the cusps, and there's some orthogonality relation. Anyway, here's what it is. If I have a formal power series like this with dm's, just some coefficients, so it's a formal power series in Q, the following are equivalent. This is the Q expansion of a modular form in a weight k on d, and this might be chi to the n here. Infinity means that it's cuspidal outside of infinity. I'm stating really the criterion we use, not some generality. So this is the Q expansion of a modular form which is cuspidal away from infinity, but is holomorphic at infinity. So it's a modular form in the standard sense. That statement is equivalent to the relation that these coefficients are orthogonal in this sense to the Fourier coefficients of every weakly holomorphic modular form like this. So what does this mean? This means that this guy is holomorphic on the interior, the upper half plane. However, it's allowed to have poles at the cusp, but because I'm restricting this to be cuspidal away from infinity, this one is not allowed to have poles anywhere except at infinity. Okay? And so you can pair any one of these guys with this series. All these pairings are 0 is equivalent to this being a modular form. And this is some kind of incarnation of Serre duality. This was observed by Borcherds and used in his paper a long time ago. Okay. So we're going to use this where you can see that in our situation we're going to apply this to our coefficients. And here, these are our coefficients. So what we're going to need is we're going to need relations of this sort in the arithmetic Chow group for every weakly holomorphic modular form of this sort. These coefficients are our m's. So this is what is going to be required. We need to show a bunch of relations like this. And those, as I say in the next part of the slide, if you know the theory of Borcherds forms, you know that to given a form like this, which usually has negative weight, we're allowing a pole, so that's not a problem. Borcherds had already constructed, in the orthogonal case, meromorphic sections of certain line bundles on the Shimura variety attached to these things. Those meromorphic sections, in some sense, are giving you relations in a Chow group. And so that's the way in which this goes. In other words, to these kind of input, we're supposed to try to create a relation in the Chow group of this nature. Okay. Well, as I say here, Borcherds had already constructed, if you take a form of this nature and you assume that the coefficients are integers, the negative coefficients are integers, or the non-positive ones, including the constant term, are integers or rational numbers which you can clear, what you get out of it is a meromorphic section of this bundle. This is basically what Borcherds did. Now, here I'm stating a unitary group analog of what Borcherds actually did. His input was similar, but he was on the orthogonal Shimura variety, and we're on the unitary Shimura variety. But otherwise, it's the same. Now, what's actually going to happen here is we're going to cheat a little bit. And the reason is we don't want to redo all of Borcherds' theory and all the calculations in the unitary case, but we're simply going to pull them back from the orthogonal case. It's good enough. And so we observe that there's a natural, if I take this Hermitian space and I take the quadratic form defined by the Hermitian form on the diagonal, that defines a quadratic form, and make the corresponding quadratic space, the signature is now 2n minus 2, 2. G tilde will be the orthogonal group of that, and it turns out there's a natural map from the Shimura variety we constructed above to the Shimura variety attached to that guy. And that means that what we can do is, for any one of these weakly holomorphic guys, as on the previous slide, we get, by Borcherds, literally, a meromorphic section of a certain line bundle on here, and then we can pull it back to the pullback of that line bundle on here, and we're going to use those forms to give our relations. As I said here in the slide, we could have done this directly using the dual pair and just redoing Borcherds' calculation, but why bother, right?
I thought that for you would be the
Sorry?
only way to go.
Sorry, what's that? If
You, that would be the natural way to go, right?
always work harder than necessary.
Mainly in his theory, you have poles where before you don't allow poles.
Right.
Usually, those are easy to regularize.
Right. Well, what you see here is that the regularization isn't so much the issue, but the control of the poles of the result is the issue in the boundary. Okay. So so this is the picture now. Now we just recall here. Now I'm being way too detailed, but so just now, right now. Anyway, the inequivalent cusps are indexed by divisors of D, of gamma 0 D. And so if I have a weakly holomorphic form, I has its normalized constant term at all the different cusps. Those numbers play a role in the answer. That's why I need to introduce them. We also have, of course, the Fourier coefficients for negative m and the constant term at 0, these constant terms. So we're going to assume these all lie in Z. That's without any loss of generality, it turns out. And so now here's the answer. So first of all, attached to this guy, Borcherds constructs a rational, a meromorphic section of a certain line bundle. We can pull it back. And what we show, first of all, is that this is actually a rational section of this bundle here, omega to the k, where k is given by the sum of these constant terms. That's the weight, that's the line bundle you have. And it's a rational section. So this is defined over k, right? So we have a rational, so this is some work here. You have to check that the meromorphic section is actually coming from a rational section. But once you have that, and you have those specifically, you know what the weight is, you can ask about its divisor on the integral model, and here's the answer. So the divisor of this guy, pulled back, made rational, on the integral model is the following. So you see it's controlled by the negative part of the Fourier expansion of f. So the negative Fourier coefficients times these total classes. Now here you notice that in particular, the total class included some of the boundary components, and so we're actually taking into account how this thing behaves in the boundary. So this is really viewing this thing as a rational section on the compactified model. So there's some boundary components here. There's some multiples of the divisor of D, which is some vertical fibers at the primes dividing the discriminant, some exceptional divisors, and here's some more vertical stuff on certain divisors. And finally, a bunch of certain multiples of the exceptional divisors, where each exceptional divisor corresponds, it's a point in the Pappus modular problem, it corresponds to a pair of abelian varieties. There's a Hom space, a little lattice, and the number of vectors of length m comes into the multiplicity of that component of the exceptional divisor. So this is, anyway, the point about writing this all up there is to say, we really know this divisor, and this was the hard work in this paper to get this actual answer. So once you have that, well, here I'm just mentioning to you what it is that's coming in here. I already did in the other slide. So you can see the different pieces that come up in this divisor. And well, the only thing that's left now is that we want to do something about the Chow groups, because we want relations in Chow hat, not Chow groups. So we get a relation. Now remember, this is a rational section of this bundle, so that divisor back there is equivalent to this bundle in the Chow group, because I have a rational section. That's in the Chow group without the hat. And now you have to put in the Green's function. And now I really am running short of time. So it turns out, so I'll just say very briefly, an idea of Brunier was that instead of taking just weakly holomorphic things, you take weakly harmonic things. So you drop the holomorphic condition, do the same lifting, and you get these harmonic, this is the input. When you do the theta lift of those guys, the regularized theta lift of those guys, you get Green's functions for the cycle. So in particular, there's a weak guy like this with this polar part for any m, and it's unique. And if you take its regularized theta lift, what you get is a log type Green's function for this cycle. That's a lot of hard work in the papers that I've mentioned here. Okay? So that's the Green's function we're going to use, and the reason for that is the fact that that defines this with the hat. So before I didn't tell you what that was, that tells you what it is. And now the main point is that if you take the weakly holomorphic guy and you take the regularized lift that we were using earlier when we were computing things, you get, in fact, the log of the norm of this section, so that these guys here, if I assemble them together, fit together into this Borcherds divisor, the log absolute value of the Borcherds section. So these are compatible. Okay. Anyway, what that means is that
if you take dV bar of this guy, it doesn't. It has some harmonicity property.
yeah, these are harmonic, yes. So you're just going to get the degree on the right-hand side of the Green's equation. You just get degree of Zm on the generic fiber. Anyway, they're completely explicitly constructed, and we can discuss characterization afterwards, right? So anyway, what do we have at this point? What we have is that we get a relation, namely this omega hat k. So you remember that this guy now is that this div hat of psi f is now equal to omega hat k because all the Green's functions have been lined up. So this is div hat means this. It's divisor together with this Green's function. And k is, as I said before. So what that means is we now get a bunch of relations like this in the Chow group, depending on these f's, which are supposed to be providing the relations. You have to use some additional facts involving Eisenstein series, and so what you finally end up with here is the fact that the phi hat minus some theta functions attached to the lattices attached to the singular points in the Pappas model, together with some Eisenstein series times special fibers, is modular. In other words, if we apply that Borcherds criterion with the relations that we've written down here with all this stuff, this is the thing that is proved to be modular. But fortunately, these things are simply either Eisenstein series, completely explicit, or explicit theta functions attached to positive definite lattices. So this piece here is modular. That's the end of the proof. Of course, now the issue is how to prove the divisor thing. And how much time do I have left? Maybe 7 minutes or something like that? 8 minutes. 8 minutes. OK, well, I can go a little slower then. Okay. Okay. So the question is, how do you prove this divisor? How do you calculate the divisor of this thing? And so, as I said here, this talk begins, as they always do, to chill you. You know, you get this chill when you see. Now we begin. There are only 8 minutes left. But I won't begin. I'll just tell you that the short point is that we're going to study this guy and the Borcherds one in a neighborhood of the boundary. And this will give us the grip on the divisor. So here's the complex situation. So I have the unitary Shimura variety mapping it to the orthogonal Shimura variety. And now you see one interesting feature here. Here the cusps, this is just on the complex points, the cusps are indexed essentially by isotropic lines. If I take the corresponding quadratic space V, an isotropic line, K line, becomes an isotropic plane. And so there's a way of associating, so each one of these boundary points here, the rational boundary points, will map to some point on a curved boundary component. It'll be a CM point on some modular curve sitting in the boundary. Now, and the Bailey-Burrell compactification, you get a CM point, as I said here, on the modular curve. Now, the one technical difficulty that arises now, which took us a whole meeting at AIM to discover we were going the wrong way to try to resolve it, is that Borcherds, when he constructs his forms, these tilde guys over here, they come equipped with a product formula. He has these beautiful product formulas which give you the most concrete description of these rational sections. The product formulas are given in the neighborhood of the point boundary components on the orthogonal Shimura variety. In other words, in the boundary components attached to isotropic lines in the quadratic space. Unfortunately, this guy never sees those points. It goes onto the inside of the modular curve somewhere. And so this goes on about that. So, well, actually in the compactification, what happens is that Again, here we blew up the point boundary components into abelian schemes, and over here in the ON2 guy, what lives at the boundary in the Bailey-Borel are modular curves. What happens when you desingularize toroidally is you get Kugasato varieties living over the modular curves. Kugasato varieties constructed in the same way B was constructed, using this extra lattice out of the standard elliptic, universal elliptic curve. So that's the map here. And so what's true is I found another product formula for this Borcherds form, which is valid in the neighborhood of the curve boundary component. Okay. And so if you look at this other product formula, you can read off the Fourier-Jacobi expansion, both of this guy here along that curve, but also therefore of the pullback at the neighborhood of that CM point. And so what you get is some multiplicity. So there's a power of the local parameter which tells you how much that divisor occurs in the divisor of this psi f. And then there are these Fourier-Jacobi coefficients, and okay, there's a formula for mult f and so on. And it turns out then that there's a so-called leading Fourier-Jacobi coefficient. So you remove the local parameter along at the neighborhood of that point, some power of it. You take then the leading coefficient here, and this is going to be a function on this abelian variety, right? Because we're looking at an expansion along this abelian variety. So this is some sort of function on the abelian variety, and it turns out the divisor of this guy is determined by the divisor of this. And then, so this is supposed to be saying that. Okay, so am I saying anything new here? Right. The full neighborhood of this, so this is a divisor in the compactification. Its whole neighborhood looks like some line bundle over this abelian variety where you take a neighborhood of the zero section and you delete the zero section. That's what a neighborhood of the cusp looks like. So it's a line bundle over this abelian variety. And the lead Fourier-Jacobi coefficient, anyway, it's a rational section of some certain bundle on here, and blah, blah, blah. One other nice thing, so I'm going to describe very roughly why it is we can get our hands on its divisor. That's the point. So the point is that remember that this divisor at the boundary in the unitary Shimura variety compactification is this abelian scheme, which is gotten by tensoring the universal CM elliptic curve with this fixed lattice. But such an abelian variety has lots of morphisms to E. Namely, if I have any vector in this Hermitian lattice, I can just take the dot product with E, or with X in this factor, and I get a morphism to E. So there are lots and lots of homomorphisms here, like this. And it turns out that the product formula for this guy that gives you a first Fourier-Jacobi coefficient. And now I'll tell you the formula. This is the last slide. Okay. So here's the formula. What happens is you end up looking at standard theta functions, the Jacobi theta function on the universal elliptic curve, and pulling it back by these various morphisms and taking products. That's essentially what's described in the model. And of course, the key here is that we completely understand the divisor of the Jacobi theta function integrally. And so then you get these formulas. The Fourier-Jacobi coefficient is some a power of the eta function, so that's just going to tell you something about, that's just a constant here, evaluated at some CM point. The vertical part, this is again just a number, but it's a bunch of, so theta is the ratio of the Jacobi theta function. This is the odd one, which vanishes at 0, and divided by eta. So this is this big theta, and there's its product formula. And so there's a constant here, which is gotten by evaluating at certain division points, not 0, fortunately, and involves these constants at the cusps of the input form. Then there's some values where I'm taking some very specific x's and doing these maps to the elliptic curve, which I described, over the things of length m inside the lattice, and weighted by the negative Fourier coefficients. And so these are all powers of this guy here, whose divisor we completely understand, and therefore you can read off completely the divisor of this guy integrally in a neighborhood of the boundary. So that's the...
And so every divisor on the bad, every component on the bad fibers meets this.
That's why Pappus is there. That's true on Pappus. It's not true on Kramer. And that's why we have both in play, because we can do this calculation near the boundary. See, these exceptional guys are living in the interior. So as far as the boundary is concerned, it doesn't matter. They're not in play, right? So we can work on either model near the boundary, and on the Pappus model, you can exactly determine these vertical components, which we're seeing here. Right. Okay, so that's it.